make Lewis structures. We're going to continue the policy or the process on and go from making the structures to seeing how they affect the different types of shapes, bond angles, polarity, etc. So the question becomes is now that we've got the Lewis structure for the molecule, what is the shape of the molecule? So to determine the shape of the molecule, we have to know how the valence electrons in a molecule are distributed. We need to know the shapes of these orbitals and what order they're occupied and how that relates. So the first method we're going to use is VSEPR, which is valence, shell, electron pair, repulsion, theory. So VSEPR is the first of the theories we're going to do. When we talk about molecules, we have three theories. We have the VSEPR, we'll get to valence bond theory, and then we'll get to molecular orbital theory. Like any other good theory, a theory explains the behavior. The problem is we do not have one theory that explains all the behaviors. Each theory explains something. So right now we're operating on three theories, but we haven't managed to come up with one theory that fits everything. So what is valence shell electron pair repulsion theory other than a mouthful? It is based upon keeping the electron domains as far as apart as possible and thus minimizing the repulsion. Minimizing the repulsions. Okay, now what does that really mean? That means that electrons are all negative, right? Everybody good with that? Just like if you took two magnets and put the norths together, they're going to try to repel. So think about it. These electron regions want to get as far apart from each other as possible. How do they do that? Now, this is a figure from a different text. And believe it or not, if you tie balloons together, you tie three balloons together, you're going to get trigonal planar. The one we're missing is tying two balloons together, which is linear. But if you tie balloons together, they automatically go in these shapes. Why? Because balloons attract electrostatic charges. So they tend to go negative, and so they tend to repel each other. So therefore, they automatically want to get as far apart from each other as possible. So the name of the game is, how far can they get from each other? Well, in order to do this, we have to look at the structure. So the first thing you've got to do, you've got to sketch the Lewis structure. We learned how to do that in the last chapter. Then the next thing is count the total number of electron regions around the central atom. Now, double or triple bonds count as one region because they're pretty much occupying the same space. If they obey the octet rule, you'll have a max of 4. If they don't obey the octet rule, you're going to have a maximum of 6 regions. Then you're going to arrange the electron repulsions in such a way to minimize the interactions. Well, what's that mean? Well, if you think about it, everything pretty much comes down to non-bonding pairs or bonding pairs and multiple bonding. Well, non-bonding pairs are going to have the greatest electron density, so they're going to push the most. They're the most negative. Bonding pairs, single bonds, are going to have the electrons tied up in between. Double bonds will have 2 sets of electrons within the region, so they're going to push more than single bonds, less than non-bonding pairs. And then triple bonds will push more than doubles. But the problem is triple bonds tend to involve linear. You can't get any farther away from each other than a 180. Okay? And so you're going to describe the molecular geometry in terms of angular arrangement of the bond pairs. So you're like, okay, these are rules. They don't make a whole lot of sense. And they kind of don't yet. As we work through the examples, you'll see how it works better. Now let's go back and define the non-bonding pairs. We said they have a higher electron density. So they're going to push or repel more. Okay, because remember, electrons are negative, so two negatives will repel more. Okay. Now, bonding pairs, remember, are in between the internuclear axis, whereas non-bonding pairs are just hanging out. They're outside the structure. Single bonds repel least. Double bonds repel more. Triple bonds repel more than doubles. And lone pairs repel the most. So if you're looking at the bond, the pushiness, and we use the term push because you're pushing groups of electrons away from each other. Kind of like playing with magnets and pushing other magnets around. That's really basically what you're doing. So when we go to talk structure, the first thing we have to do is talk about the arrangements that are possible with respect to angles. So what we're looking at is this is electronic structure. And with electronic structure, you get angles. So if you have only 2 electron regions, the farthest you can get from each other is 180. Now, it doesn't matter if you were to have a triple bond over here and a single bond over there. You can't move any farther apart than 180. Okay, that's not an option. If you put 3 in a plane, it's called trigonal planar. And no, you don't get this list to take the test. So but it's really simple because if you think about it, you're going to get a triangle. So that's the trigonal and it's flat. So that's the planar. So trigonal planar means that you're going to have a flat triangle. And if you have a flat triangle, because the circle is 360 degrees, each angle is 120. Now, we'll look at where, if you have a non-bonding pair and 2 bonding pairs, you end up pushing the angles around. We'll look at that in a minute. Okay? The next, and that's if you have 3. If you have 4, you have a tetrahedral. And everybody's like, what? You have that? Well, if you think back to geometry, a 4-sided figure is a tetrahedron. Now, rectangles or squares are forms of tetrahedrals, but tetrahedrals are 4-sided figures. So the thing about a 4-sided figure is it's in 3 dimensions and you're looking at it in 2. So the easiest way to draw it is with 2 items in the plane. And so if you play the 3D game, then you have 2 in the plane. Then you're going to have one going back and one coming towards you. So this is called the line wedge. You can also do the dash wedge. The dashes are hard to see. So these are the four groups that you can have when you have a tetrahedron. And this is how you can designate 109.5. With the trigonal planar, you can designate the 120 here. Okay, now, I'm going to go back real quick. These are the ones that obey the octet. If you exceed the octet, you're going to go into these two. The first region is with 5, and it's trigonal bipyramidal. And so basically it's bipyramidal, it's two pyramids with a triangular base. So the easiest way to draw this is like this. Okay, I don't like that way it worked out. So let me draw my triangle again. We have our triangle with it coming up and it going down. And we're going to discuss axial and equatorial in just a minute when we discuss this. But this is basically what this shape is. So I'm going to leave that one alone, and then I'm going to come over here and I'm going to show you if you draw lines down to each of these points from here and then back up, then what you're ending up with is a pyramid that's got a triangular base stacked on top of a second triangle, hence the trigonal bipyramidal. Now, the trick to this is these angles, since it's a triangle, are 120, but these angles are 90 degrees to the plane. So this one, you have to designate which species is going where to designate the angles. More about that shortly. Now, the last one is if you have 6, it's an octahedral, which is basically a square going up and down connected, and it's a pyramid with 4 sides, basically. And so this shape geometrically is octahedral. And all the angles here are 90 degrees. And remember when I told you that if you have a linear and it's 180, you can't move 180, you can't move 90 either. These things are so close together that even if you have a lone pair, it's going to position differently, but you're not going to change angles here. More about that in just a minute. So we've set up our electron geometry here. So we take it from electron geometry to molecular geometry, and you're like, well, what's the difference? Well, one of my favorite commercials on TV is that Windex commercial. You know, the one with the 2 birds sitting in the tree and discussing the fact that they can see inside the room, and it's like, don't go there. You can't make it in. There's something in the way. Well, when you talk about molecular shape, all you see are the atoms. So atoms are the only visual in the molecular shape. In the electronic shape, we're looking at electrons, so we don't care if they're bonded or non-bonded. So in molecules, we only see the atoms in the structure. So the question is, well, do we just throw out the lone pairs? No. The lone pairs are like the glass. The birds know they can't get inside because there's something in the way, but they cannot see it. So I refer to the lone pairs as glass because they have an effect on shape, but you can't see them. So as we go through, if you have 2 bonding pairs and 0 non-bonding pairs, then you started off with linear as your electronic. So you're going to end up with linear as your molecular. So here we have trigonal planar as our electronic. And so we can have, if we were to have 2 bonding pairs, one bonding pair and 2 non-bonding pairs, then you end up with a linear, and you can't have that. But if you have 3 bonding pairs and 0 non-bonding pairs, then you're still going to be trigonal planar. However, if you end up with 2 bonding pairs and a non-bonding pair, then you're going to end up with it bent. The other thing is because this is a lone pair, it's going to push more, and this angle here will end up being less than 120. So we're going to talk about angles as we go and as we get into molecules. So with 4, electronically, and yes, you're going to have to ID both the electronic and the molecular structure, you're going to get tetrahedral. So again, if you have 4 bonding, 0 non-bonding, you're tetrahedral again. If you have 3 bonding and 1 non-bonding, you're going to end up with trigonal pyramidal. That's like ammonia. So again, what you're dealing with is a lone pair up here. Again, you don't see it, but it has an effect. And so what it'll do is make all these angles be less than 109.5. Because what it's going to do is push. If you have 2 bonding and 2 non-bonding pairs, water, then you have a bent, because all you don't see the lone pairs. And so this angle here is going to be much less than 109.5 because you have not 1 pair but 2 pairs pushing. Now, this slide, with me not writing on it, is in your blank sheet that's handed up, and you may want to go ahead and keep a copy. Well, you can always download a blank copy. So the bottom line is these are handy to have, especially when you're doing the lab. Okay. So here we're moving up to 5 regions. This is trigonal, bipyramidal, electronic. And so again, when we have 5 bonding pairs and 0, notice they match. The trick to this one is that the bond angles are less in the triangle in what we call the equatorial position. More about that one on the next slide. And well, let's bounce forward and come back. Okay, here we go. This is the trigonal bipyramidal. And if you notice, it's the triangle. This is kind of like the center of the molecule. We call these the equatorial positions. They're on the central plane of the molecule. These positions are axial. These are above and below the plane. And because this is got a 120 here, but these are always 90, think about it. If you're in the 120 position, are you farther away from everything than the 90? Yes. So what happens is lone pairs are first going to go to the equatorial positions first. This is actually critical because it makes a difference in the shape. So now that we understand equatorial and axial, then if the first lone pair goes in here, so that makes it a seesaw. Now, this one drove me insane when I was in chemistry. I could not figure this out. If you can make this with a model kit and put it on its side, it's a seesaw, like a teeter-totter. Not, you know. So anyway, that position is seesaw, knowing it's going to go equatorial. If you put in 3, two lone pairs here, they're both of them are going in the equatorial. And so all you're left with is this molecule here, so it's T-shaped. If you replace all three with lone pairs in the equatorial position, you have two atoms above and below, so it's a linear molecule. Even though electronically it's still trigonal bipyramidal. Okay? So here's octahedral electronically. So if you have 6 and 0, again, same name. If you have 5 bonding and 1 non-bonding, the non-bonding pair is going to go in any position, it doesn't matter. And what that does is it leaves you with a square pyramid. So it's square pyramidal. If you put in a second one, you have to put it in opposite. So if here's the first lone pair, the second one's got to go in opposite. So that leaves you with a flat plane, so square planar. Now you tend to not go past that with the problems that we're going to have you do, but we are going to have you draw Lewis structures and start identifying molecular, electronic, molecular, and shapes and angles. Okay, so this is the slides that I came up with. Okay, here's the one we went over already. There's tables in your text that have pretty much the same thing on it. If you prefer that version, you can Google it and find lots of variations online. I would stick with either mine or the text only because you could have slight variations and I don't want you going there. Okay, so we're going to use the VSEPR model to predict the electron pair geometry, molecular geometry, and the bond angles. Okay, so what we're going to do on this one is this is similar to how it's going to be on the exam, except you're not going to necessarily draw it out. I mean, you are going to draw it out and submit those, but then I'll ask the questions multiple choice. And here are the questions that are going to be asked. The first question is going to be electronic shape. The second question will be molecular shape. The third question, and I don't know when I started using III, were the bond angles. The fourth question is the polarity, which we haven't done. And the fifth question will be hybridization, which we really haven't done. So the point being is I'm going to go ahead and list them. We're going to do the first three. Then we're going to go ahead and talk about the other things. And then I'm going to come back to what we've done before. With any luck, I will be able to upload the images. If not, I'll have to redraw them. But we'll put all this together for you. So don't worry about the fact that we can't do but the first three right now. So I'm going to draw the structure. So boron is 3, chlorine is 7 times 3, which is 21, so we're 24. Boron's the central atom. So I have chlorine, chlorine, and chlorine. So that's 3, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we're good. So now what I'm going to do on this first couple is I'm going to count regions. So we got 1 region, 2 region, 3 regions. So we're back to, we have 3 electron regions. Okay. So now let's start answering the questions. So electronic shape with 3 regions is trigonal planar. Since all of the electron regions are bonding and there are no non-bonding, then the molecular shape is trigonal planar. Since all the bonds are the same, then all the angles are 120 degrees. So if they weren't, or if you wanted to draw it in, you could draw it in like this. Okay? So we're good on that one. So let's go to the next one. So we have 4 plus 4 times 7, which is 32 electrons. So I'm going to start with the fluorine on top, so I would leave enough room. So we have 32, so it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So again, I'll highlight it, and this is region 1, 2, 3, and 4. So we have 4 electron regions. That means when we go to do the shapes, we have tetrahedral. The electronic shape, the molecular shape is tetrahedral. Because all the bonds are the same, they're all 109.5. Now, if you wanted to draw that in, you could draw it like this. And that's fluorine, that's fluorine, that's fluorine, it's fluorine, and you could just put in that they're 109.5. Okay? So far, so good. And remember, I've left the list at the bottom. We're going to do that for all of them. So selenium is, I think that's under oxygen, but I'm going to double check. Yep, it is. So this is 6, whoops, it's hard to do this when you're not drawing. That's weird. Okay, so this is 6 plus 6 times 7. 6 times 7 is 42, plus 6 is 48. So selenium will be my central. There are 6. So I'm expanding it out. So 2, 4, 6. Well, that one is crazy looking. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's actually 2. 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48. Now, some of these look a little bit goofy because of like the north, south, east, west, and I got a little wonky. And that's okay. You can see where the bonds are, etc. So on this one, if you look at it, you have 6 electron regions. Everybody good with that? That means that electronically, this is an octahedral. The shape-wise is octahedral. And that makes all the angles 90. Now, if for some reason you wanted to draw them in, you could do the square with the up and the down, and you can say 90, etc. So these are all 90. So we're going to leave these, continue on, do some more. And as I said, once we do polarity and hybridization, we will come back to these. So let's go into the next realm here. We have iodide, which is 7 plus 3 times 7. So that's 4 times 7, which is 28. So iodide is the central. You got fluorine, fluorine, and fluorine. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Remember the rule is put anything left on the central atom, even this is extra. So that was 24. So we have 26 and 28. So here we go. Let's count electron regions. This is 1, this is 2, this is 3, this is 4, and this is 5. So we actually have 5 electron regions. So having said that, then let's look at our shapes. If we have 5 electron regions, our electronic shape is trigonal pyramidal. And I'll be honest, to me this is easier to draw in. So we have the triangle with the up and down. Now remember, when we have lone pairs, they've got to go in the equatorial position. The fluorine is going to go here, here, and here. So if we look at it, then the only thing we're really going to see is that right there, which this is in 3D, so it's going to appear like that, which means this molecule is T-shaped. Now, the bond angles, these are going to be 90 here to the plane, and since you're only going to be able to see the atoms, you only have to worry about those. But just remember that these electron pairs are going to push back and forth. This is going to be critical when we see something that doesn't have as much. So we've got the angles in there. Those are 90. The angles associated with the equatorial position would be 120. But we don't always see those. All right, so tellurium is, again, 6 plus 4 times 7. 4 times 7 is 28, so this is 34. So we'll start with tellurium, fluorine, 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 fluorine. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 2 left over, so they've got to go in a new position. So that's 34. So if you look at it and you count electron regions, you have 4 bonding and 1 non-bonding, so you're back to 5 regions. So when you look at the shapes, this is going to be trigonal, bipyramidal, and I just realized, I looked over here, this is trigonal bipyramidal, not pyramidal. So we have trigonal bipyramidal, and so when we look at this one, we have that here. Your lone pair is going to go here, your fluorine here, 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 and here. So if you look at it, it's going to be seesaw because we've got a non-bonding pair. And so what actually happens here is these bond angles here are going to be 90. They're not going to move. 90 can't move. But you've got an angle here between these 2 fluorines. Now, it should start off being 120. But remember, you're going to have the lone pairs push. So this angle between the 2 fluorines is actually going to come out to be less than 120. Do you know exactly what it is? No. And do I care? No. So do not look it up and then write it down, because I don't care. I only want to know whether it's, 120, 109.5, less than or greater than, okay? So here we have, notice that our angles are above, and I'm writing that in so you can know that we didn't skip it. Okay, that brings us to our last one, which is 4 plus 2 times 6, which is 12, so that's 16. So we're going to have carbon, sulfur, sulfur. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, there's a variety of ways that we can draw this, but we're going to go with the simplest one, which is sulfur double bonded to carbon on both sides. And in that case, does it matter if you have 2 double bonds or 1 double bond, a single bond and 1 triple bond? No, because the electron regions don't change. So we have 2 electron regions because remember, multiple bonds count as a region. So if that's the case, electronically, we're linear. Molecularly, we're linear as well. And here's the real kicker. If you're linear, your angles are 180, and you can't move 180. So on this one, we're good to go. So if you've noticed, we've looked at this we've drawn the Lewis structure. Then from the Lewis structure, you count the regions. That gives you the electronic. From the electronic, you see how many are bonding and how many are non-bonding. That gives you the molecular. The angles come from the electronic. So if you're trying to determine the electron or the angles, then you go back to the electronic structure. So we got 2 more to go, and these are ions. So 10 is 4 plus 3 times 7, so negative plus 1. So 21 plus 5 is 26. So we've got 10, and we got chlorine, chlorine, and chlorine. Oh, I forgot to count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Guys, I didn't forget to count. I was just doing it in my head as opposed to out loud. This is negatively charged. It's an ion, so we're going to put that as our negative. So when we look at it, we've got 4 electron regions. And if you don't see that, that's 3 single bonds and 1 lone pair. So when we do this, again, we come into, again, the electronic structure, the molecular structure, and the bond angles. So if we have 4 regions, electronically, it's tetrahedral. But if you look at the tetrahedral, you have chlorine, 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 and the lone pairs here. So what's going to happen is this is going to push down here. So you're going to end up with these 3 kind of coming in as a triangular base. And so it's trigonal pyramidal. These shapes are not pyramidal, are not bad if you take them apart and look at them. And then the bond angles, since we know that one's going to push more, what that's going to do is make these angles here less than 109.5. Don't know exactly what they are, don't care, but angles see above. Do not forget them. Okay, now for H. We have xenon, and you're like, wait, this is a noble gas. Yes, they can make a few compounds from them in the lab. This isn't naturally existing. Plus 5 times 7 minus 1. 5 times 7 is 35, minus 1 is 34, plus 8 is 42. I think it's 42. So we have, and I'm going to start with a fluorine at the top so I can get my spacing. So I have 1, 2, 3, erase that, 4, 5. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and 42. Did I do that right? Yep. So, and again, it's a charged species, so it's going in a block. So when we look at this, we have 5 bonding regions and 1 non-bonding region, so we have 6 electron regions. Which means that electronically we have 6 regions, so it's an octahedral. And again, if we look at it like this, one of the lone pairs is going to go at, it doesn't matter what the first position is, it's easier if you write it as if it's actually equatorial. So then it's square pyramidal. It's a pyramid with square base. And all the angles are 90 degrees because you can't move 90. Now, this would like to push more, but it has nowhere to push. It's kind of like getting crammed in the back seat of a car and you've already gotten the maximum number of people in there, so that if somebody else gets in, you can't push any farther to let somebody else in. Okay? So, at this point, we have got the electronic, the molecular shapes, and the bond angles. I have left room because we're going to come back once we address hybridization and polarity and add them back in to these structures. Okay? So make sure you keep up with these and they're clean and neat and you can add more to them. Okay? We'll continue on in the next section.